while, right? Almost 3 weeks. Okay. Okay. I thought I sent an email, but I think I didn't. But I meant to send an email to say that, to remind you that we have a class on June 21st, which is a Saturday. That's a makeup class. And we have an exam on that day as well. And it's fourth period, and I don't know the room yet. They didn't tell us the room yet. What? Programming, yeah, I'll send you that, the room number. I mean, the period. I'll send you the period. So anyway, and the exam will cover, not too much actually. I'll make it kind of light exam. So the exam will cover, actually I think maybe I didn't do it, but I wanted to, so you guys had some homework that was due like a week ago, right?
Yeah.
Now what I'm going to do is extend that, so you can work on it again if you want to. You don't have to, but I'll give you an opportunity to work on it until June 15th, and you'll have like 4 more tries. You know, usually you have 6 tries, so you'll get 4 more tries. And the reason I'm doing that is because, you know, that was material that we really didn't cover in class, so actually I prefer that we cover it in class before you have to finish it. But there are other teachers that make the students do stuff without covering it in class. And that might be a good exercise sometimes, but I don't usually do that. So I'm not going to really do that this time, so you'll have some more chances to work on that. And then also I'm assigning you homework for this week. And in our next class, I'll also assign you homework. So the test will be on those assignments only. So in other words, I'm extending the due date of last time's homework till like this Friday. But that will be included on the exam, that material, plus the homework that you have due for next week will also be on the exam. Will also be included as material, possibly on the exam. And then next week, I'll also assign you some more homework, and that will also be. So it's basically like 3 sets of homework will be what the exam will cover. Okay, so it's not everything that we've done, it's just those 3 sets of homework. Okay? So I'll try to send you an email to explain that again. Okay? So does anybody have any questions about that or anything else? Okay. All right, so then I thought I should cover that material maybe that you did before, that you tried to do homework on before this past week. So let's do a little bit of that. So let's start out with this function. So the topic that we're covering is called limits. The topic that we're covering is called limits. So let's think about, here's the example that might be useful for discussing limits. So suppose we have a function and this function. So this one is a kind of a good function to talk about limits, to introduce the idea of limits. So anybody want to, and does that function suggest anything to anybody? Like, well, you know, I don't know. Anything anybody want to say to do about that function? Or no, nothing interesting about this function at all. I mean, it doesn't. Anyway, so you know, most people will say, "Oh, this is equal to this." Right? Most people will do that, right? And then most people will do this also, and they'll get this, right? So that means, well, by the way, when we do that, when we say one function equals another, that means that for any value of x, they should produce the same result. So let's see if that's true. Let's try x equals 0, let's try x equals 1, let's try x equals 5, whatever. Let's try a few and see. If these are really equal, I mean, if this is true, if we didn't make a mistake, then if I put in a number for x here, I should get the same thing as if I put in a number for x there. So let's just see. How about 0? What do I get when what do I get over here when I put in 0? Of course I get 2, right? Now what do I get here? Get minus 4 over minus 2, which is also 2, right? So it worked then. Okay, let's try 1. Put 1 in here. What do you get? 3. What do you get here? You get 1 minus 4 is negative 3 over 1 minus 2 is negative 1. Negative 3 over negative 1 is 3. You get the same thing, right? And if we try 5, let's just try 5. What do you get here? 7. How about here? 25 minus 4 is 21. And 5 minus 2 is 3. So 21 over 3 is 7. You get the same thing. Okay, so yeah, it looks like they're the same, right? Except for one place, right? There is one place where they aren't really the same. And where is that? If you put in 2 here, we have to say, no, we can't do that. Right? We're not allowed to do that because we'll get 0 over 0, so we're not allowed to do that. Right? So this function, we will say it's not defined at 2, but you wouldn't say that about this. Right? So they're not the same everywhere, but they're the same everywhere except when x equals 2. Okay? So if you want to say equals, 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 you really have to say as long as x is not equal to 2, right? Then it's okay. Okay? Okay? Are you talking on the phone? Okay, so, does everyone agree with this? Now, okay, so how about if you want to graph these? If you want to graph this one and this one, so what does graphing mean? It means like basically you say y equals that, right? Or it's like saying y equals that if you're doing this one, right? So, but this one is so easy to graph, right? I hope it's really super easy for everybody. So if you're going to graph it, it looks like it crosses the y-axis at 2. And it has a slope of 1, right? There's a slope of 1, right? This is slope of 1 here, right? So it just looks like this, something like that, right? Okay? Now, if this produces the same value, whatever x that I put in, as that does, then this should have exactly the same graph, right? Of course. Right? So, this should have the same graph as that, except that what? Except this one is not defined at 0, at 2. So, we have to do what? We have to indicate that somehow. And usually, the way that they indicate that is they put a circle there. Okay, and that means it's not defined there. Okay? So that would be the graph of this one. Okay, everyone agree? Now, if we are talking about this one, what is the height of that point? When x is equal to 2, what's the height? 4, right? When x equals 2, of course the height is 4. So this is 4, right? Just let's put that in there. Okay? All right, everybody happy with that picture? Okay, now, suppose that, I had this function. I'm not, like I'm hiding it from you. And I'm not telling you what function I have in my pocket or I have in a little plastic bag. I'm hiding it from you. And you're allowed to ask me questions about it. The kinds of questions you can ask me are, so let's make this into a game. So the kinds of questions you can ask me are, you can give me the x value and I have to tell you the y value. Okay? All right, so for example, you'd say, okay, the x value is 0, what's the y value? So what would I say? When the x value is 0, the y value is what? 2, right? So that's the game. Okay? So you don't know what function I'm talking about, but you can ask me those questions and I have to tell you the answer. Okay? Now, another second part of the game is that you can't ask me what the value is at 2. Okay? But you can ask me as close as you want to 2, but not at 2. That's one of the rules of this game. Okay? So your goal is to guess the value at 2. Okay? So this is the game. Okay? Your goal is to guess the value at 2. So what are you going to do? How are you going to start to guess? You can't ask me the value at 2, I won't tell you. But any other value, I'll tell you. So you might say, okay, what's the value at 100? And I would say what? 102. But that wouldn't be really useful for you, because that's really far away from 2. That's not very, right? That's not really going to help you guess what it is at 2. So what kinds of questions would you ask me? You probably wouldn't ask me about 100, right? What would you ask me? 0, okay, you would ask me 0, and I would say 2. And then, is that going to be sufficient for you? Because you can do this as much as you want. That's the game. Okay, what else? So would you ask me another question? What? Okay, good. Well, before we get to that one, you might say 1. If you said 1, then what? I would say what? I would say 3, right? Okay, you'd say, okay, that's kind of good. But it was 2. When it was 0, it was 2. When it was 1, it was 3. Okay, then somebody said, well, how about 1.9? You'd say, okay, I think I'll ask him at 1.9. And what would I answer in that case? 3.9. Okay, and then she said, how about 1.9999999? And then I would have to say what? 3.9999999, right? Okay, and now, okay, you want to ask me another one before you make it a guess? Yeah, maybe. You might say, how about how about 2.1? And what would I say? 4.1. So I said 3.99999, and I said what? 4.1. And then you might say what? 2.00001. And then I'd say what? 4.00001, right? Or whatever. Right? And so you could keep doing this, and my question is, if you did it enough, what would your final guess be? What would you, so after you've asked enough questions, you'll get tired of asking the questions, and you'll say, okay, I'm ready to guess. Okay, and finally, what would you guess the value is at 2? What? 4, right? That's what you would guess, 4? Right? Everyone agree? And that's called the limit. The limit at 2 is called 4. Is 4. Okay? You understand? So that's what we mean by limit. Do you understand the game that we just played? Okay? And the way we write that mathematically is we write the limit And the way we say getting closer and closer to 2, but not at 2, right? Getting closer and closer to 2, but not at 2. The way we say that is like this: x, arrow, 2. So that means not at 2, but getting closer and closer to 2. Okay? And then you have to, of course, you have to mention the function that we're talking about. Otherwise, this doesn't make any sense. So we were talking about this function, for example. So you have to write it, and you write it here. That's the way the function goes. Okay? And then your guess is you write here. So what was your guess again? As x gets closer to 2, what would you guess? The height is 4, right? So you put that here. Okay? Do you understand? Now suppose the function wasn't this function, but this function. First of all, is that really a function? So you have to go back to how you learned about the meaning of functions. So if you took fundamental math, they should have spent a good amount of time on that. Or if you studied somewhere else, you should have learned it also. But I'll just remind you that the idea is that a function is like, if you're talking about a graph, any graph is a function as long as there's no place where when you put in a value for x, you get 2 values out for y. In other words, if you had a picture like this, like that, that's not a function. Because if you put in this value of x, say 3, you get this value and this value. You get these 2 values out. That's not a function. As long as you don't get that, we call such a graph a function. That's the definition of a function. You might say that's weird. Why do we bother making such a definition? I'm not even sure why we do. I think I know why, but it's kind of arbitrary. It's basically an arbitrary thing. But anyway, that's the definition. And if you're thinking about it in terms of a graph, that's the definition. Okay, so that's the definition of function. So if you put in one value and you can get 2 different heights out of it, that's not a function. But if that doesn't happen, that is a function. So another example would be this. Just those 3 dots are a function. So if you put in a value here, you get just 1 value out. If you put in a value here, you just get 1 out. You put a value here, you just get 1 out. That's a function. But this set of 4 dots is not a function. Because now if you put in this value, you get 2 heights out. That's not a function. Okay, so that's just the definition of a function. Nothing to argue about there. That's just the definition. So this is not a function, but going back to my statement, suppose we had this picture, and first I want to verify, is this a function or not? So is it or not? Are there any people that vote to say no? Okay, so this is a function, right? Because here, if I put in 2, what height do I get out? What? No, not 4. What do you think this circle means? What does that open circle mean? That just means it's not there. I mean, that's the way we indicate. We need some way to indicate that it's not there. So that's what somebody made up as a way to indicate that it's not there. So what is the height at 2? 6, right? In fact, if you wanted to write this, you'd write f of 2 is equal to what? 6, right? That means that the height is 6. Okay, so first of all, you should understand that. Okay? But that's not really what we're talking about. We're talking about limits here. So, so I'm saying, suppose we had this, before we said this, and I said, what was the limit as x approaches 2? I said, what was this? And the answer was what? 4. Now, I changed the picture to this, and I asked the same question again. What's the limit as x approaches 2? Now, wait. Before, f of 2, before, we would say, is not defined, right? f of 2 is not defined in that picture, right? But now, I write that, I don't say that anymore, right? F of 2 is not defined. Now I say what? F of 2 is what? What is f of 2? 6, right? The height of the function when x equals 2 is what? Is 6, right? Is that clear? Everybody knows this, right? Okay, you're supposed to know this. Okay? Alright, now, so this is a function, a different function from the original one. And now I'm still going to ask the same question though. So I guess I can't use this because this is not the same function anymore. So I'll just call it f now. It's not x squared minus 4 over x minus 2 anymore, so I can't put that in there. But that function there, that picture, I'll call it f. Okay, so what's the answer now? Okay, I asked a new question, right? Everyone agree that I asked a new question? Right, the answer to the other question, we already did it. But now I have a new function. I'm asking the question about this function. Okay? Now you have to think about how I described the way to answer it. And how did I describe the way to answer it? I described it as though it were a game. Right? And what was the game again? You're allowed to ask me as many questions as you want, and I have to answer them. But I won't tell you the answer exactly at 2. And then your job is to make a guess. Now, I can't believe that anybody would guess 6. Right? Nobody would guess 6, right? There's no reason to guess 6. Right? So what would you guess? 4. And that's the answer. So this is still 4, right? If the game is as I described, nobody's going to guess 6. Right? So that's what this means. Okay, do you understand? Okay? So it doesn't matter so the point is that when you're talking about a limit, it doesn't matter what it's equal to exactly at the place. It's only what the pattern is as you get closer to that place. Okay, that's the idea of a limit. So I'll say that again. When you're talking about limits, it's not what's happening exactly at the place. So this is the place, you put the place here. So it's not what's happening exactly at 2 that you're interested in. If you want to know exactly what's happening at 2, how do you ask that question? You say, what is this? That's how you ask that question. So we already have a way to ask that. This is a way to ask a different question. And what's the question here is, what's happening as you get closer and closer to 2? Okay, so if you want to be able to ask that question, you have to write it like this. Okay, if you just want to know what's happening at 2, you can just do that. That's a much simpler thing to write. So we already have that, so we don't need to be redundant and do the same thing again. This is a different question. Okay, do you understand? So, in other words, why you say, well, who cares about this? It's kind of a weird thing. But so you could say that, how about, if I told you for this one, if I told you for that one, you said, what's going on at 2? And I said, if I just told you, it's not defined. Which would you rather know? That it's not defined, or that it's not defined and the limit at 2 is 4? I mean, which is giving you more information? The fact, if I just say it's not defined, or if I say it's not defined and this, which gives you more information? Obviously, this gives you more information, right? This kind of gives you a kind of a lot of information, right? I mean, it tells you that there's a very strong pattern happening. Now, it doesn't tell you that it's going like this. Maybe it looks like this. something like that. Okay, so it doesn't nail it down completely, but it still gives you a lot of information. So telling somebody about the limit does provide extra information, therefore it's useful. Okay? But that's what it is. Okay, do you understand? It's explaining what you would guess if you played that game. Okay? That's what the limit means. And the way you write it is like this. So what you put here is what? In this notation, what you put here is what part? What you're getting closer and closer to on the x-axis, right? Right? And what you put here is what? The particular function that you're considering. Right? And what you put here is what? The height that the function is getting closer and closer to. Okay? So you've got to get used to this notation. I realize that it's not, maybe you haven't seen it before, so you're not so used to it. So, but let's just repeat it one more time. What you put here is what? The place that you're getting closer and closer to on the x-axis. And what you put here is what? The particular function that you're interested in. And what you put here is what? The value that you say it's, the value that you would guess, or the height that it's getting closer and closer to. Okay? Now, how about, so we know, let's call this function g of x, and let's call this one f of x. So we already said that g and f are not exactly the same, right? They're almost exactly the same, but they're not quite the same, right? Because this one is not defined at 2, but this one, oh sorry, that's stupid. Sorry. Alright, this is g, and this is f. We already said they're not exactly the same, right? Because this one is not defined at 2, but this one is defined at 2. Okay, now, however, how about this? So g of x is not f of x, right? Not exactly. Not perfectly equal, right? Not exactly the same, right? You have to agree with that. However, how about this? Well, I'm sorry, before we do that, before I ask you that, let's draw g of x. What does g of x look like? Looks like that, right? Okay? Before I do that, before I ask you this, what is this? What is that? So if you think of it as the game, again, the same game again. So what's the game? This is G. So what's the game? You can ask me anything except for at 2. And then you guess what you think the height is. So what would you guess? 4, right? Right? 4. So what is, so the limit of, so this one is equal to what? 4, right? And this one we already said is equal to what? 4. So their limits are the same, right? Why? Because it doesn't matter at the exact point what their value is. That's not what the limit is concerned with. Okay, so it seems like a very weird, why is anybody doing this? But that, you just have to learn it for now. You just have to accept it for now, because we will have a use for it. Okay? So, again, so what is this? 4, and this is also 4. Because the limit is not concerned with what's happening exactly, in this case at 2, but what's happening closer and closer. We can say infinitely close to 2, but not 2. Okay? So mathematicians starting around, well, around Newton's time, and even some Greek mathematicians, they were trying to figure out the area of a circle. That wasn't a very good circle. The area of a circle, that's not a very good circle either, but they were trying to figure out the area of a circle, and the way they started to do it was they started to inscribe things like this in there, and then they put more sides in there, and more sides, and more sides, and they kind of were thinking about this idea of having infinitely many sides, and that was, they were confronting this idea of having an infinite number of things. That was the Greeks, and then when Newton, Isaac Newton, who was the inventor of a lot of physics, he also became needed to think about this idea of kind of infinitely close to something. And so that's where these ideas came up. Okay, so there was a reason for them. But we're asking kind of, if you could get infinitely close to 2, but not at 2, that kind of question. Okay? So that's where this comes from. All right, so that's the idea of a limit. Okay, does everyone have a basic feeling for this now? All right, let's do some of the problems again that you may not have done. What happened? Okay. All right, so let's go through some of the homework. Which one did we do last? This one? Limits graphically, or no? Yeah. This one. Okay, so let's look at this. So, what's the function that we're examining in this limit question? What's the function? So the function goes here, so this is the function, right? So what is it? X minus 12 over x minus 2. Okay, that's the function. And where are we interested in checking it? At 0, right? Okay. And how are we going to find out what it is? Well, we have to put in values that are close to 0, right? But this one, you don't have to really do too much work, actually, because there's no real problem at 0, right? You know what I mean? Like, the one we had here, there was a problem at 2, right? What do I mean by there was a problem? It wasn't defined at 2, right? But this one doesn't have any real problem at 0, so really, yeah, you can do that game that I was saying. Like, you could put in 0.1, 0.11, 0.01. You can choose values that are very close to, but actually all you have to do for this one is put in 0. I don't know if you can see that that's true, but I don't feel like doing the other stuff, so I'm going to do that. So what do you get if you put in 0, by the way? You get 6, and that's actually going to be the answer. All right? That wasn't so interesting. Okay, now this one, though, does have a problem at 4, right? So the denominator will be 0 there, right? Right? So, but you can estimate it by putting in values that are close to 4. Now, what are you going to get in this case, though? When I put values that are close to 4, what's the denominator going to? what's going to happen to the denominator? Is it going to get big or small? If I put in 4.1, what am I going to get here? No, if I put in, yeah, but if I put in 4.1, what am I going to get on the bottom? 0.1. Is that big or small? Small, right? What if I put in, what did I say? 4.1. If I put in 4.01, then I'm going to get 0.01, right? Which is even smaller, right? So as I get closer and closer to 4, this number on the bottom is going to get smaller and smaller, right? Agreed? Now how about the number on the top? What's going to happen to that? As I get closer and closer to 4, this is going to get closer and closer to 16. Minus 6, so that it's going to get closer and closer to 10, right? So on the top, it's going to be getting close to 10. But on the bottom, it's going to be getting smaller and tinier and tinier and tinier, right? So what happens to something like that? When the top is like just a regular number like 10, and the bottom is getting very close to 0, what happens to the whole thing? It's getting huge, right? Right? It's going to infinity, we say. Okay? So in that case, you can say this. Okay? So you can say that, infinity. You can type in the word infinity. Okay? Does everyone understand that idea or not? Anybody not understand that? Let's say it one more time. If we're asking when we get close to 4, when we get close to 4, what happens to this piece? It's getting close to what? 16, right? Right? And then, so 16 minus 6, that's getting close to 10. But this part is getting close to 0, right? Right? So you're getting something like 10 over 0, which is infinity, right? You're going to infinity. So the answer would be infinity. Okay? Now how about this one? Let's try this one. What happens in the bottom as you get close to -3? Huh? The bottom gets close to 0, right? But what happens to the top? It's 9 plus 3 is what? 12. So you're getting something like 12 over 0, which is big or small? Very large. It's infinity again. Let's see what he says about this.
Estimate the limit numerically. The limit as x approaches -1 of x squared plus 1 over x plus 1. So we cannot simply plug in -1
That's this -1.
because we'll get 0 in the denominator of the fraction. So we need to use a table of values, and we're going to plug in values that get very close to -1 from the left and the right. So in doing so,
so what he's doing is making a table of what we did. I said,
we use -1.1,
is it like 4.1, 4.01, 4.001. He's
we
just
use
writing it down.
-1.01, which gives us -202.01, -1.00.
Where is he getting those numbers, like this number here, -22.1? Where's that coming from? He puts this into all these values, and that's what he ends up getting. Okay? Where does he get this number? He puts this for x into here, and he gets this. Okay, does everyone understand? And why is he choosing this number, then this number, then this, then the next number? Why is he using these numbers? Because these numbers are getting closer and closer to what? No. Getting closer and closer to -1, right? This is closer to -1. The next one,
1.
this one is even closer to -1, right? So he's just using values that are getting closer and closer to -1, and he's checking what does this function give us. Okay, everyone understand?
Which gives us negative 2002.001, negative 1.0001, which gives us negative 20,000.
So why does he choose this number again? It's getting closer to negative 1, right? We start out here, we're getting closer and closer to negative 1. That's what we're interested in.
Negative 1, which is undefined because 0 will be in the denominator. Negative 0.9999.
Why does he choose that number? This is also close to negative 1, right? This is a negative sign there. This is also close to negative 1, right? So he's checking all these numbers close to negative 1. Now, are these numbers getting closer and closer to a single number? No, they're just getting bigger and bigger, right? So in that case, the limit is said to be infinity. Okay, now we didn't have such a picture in ours, right? I had the limit was what? 4, right? Here, the limit was 4. We didn't have anything where it was getting bigger and bigger. But in this case, this function, it's getting bigger and bigger, right? We can't change that. That's what it is. Okay, so this function is just getting bigger and bigger as x gets closer and closer to negative 1. So the answer isn't going to be like 4. Okay, the answer isn't going to be like 4. It's going to be, we just have to say, oh, it's just getting bigger and bigger, period. And so the way we say that is, we say infinity.
Which will give us 19,998.0001, negative 0.999, which will give us 1,998.001, negative 0.99, which gives us 198.01.
Now he's kind of going backwards here, but I see what he's doing. He's going, these are getting closer to negative 1, and then he's saying, if you go this way, it's also getting close to negative 1. So the two closest numbers to negative 1 are this one and this one. But okay.
And negative 0.9, which gives us 18.1. So as we can see from the table, at negative 1.0001, we have negative 20,002.
Okay, so I forgot to mention that this is negative. I forgot to notice that this is negative, whereas this side it's positive. So, okay, let's see what he says about that.
At negative 0.9999, we have positive 19,998.0001. So our values are going to two different places for f of x, one being positive and one being negative. So therefore, the limit does not exist.
Okay. Okay, so in that case, I said, what did I say just before? I said we should call it infinity, but I was wrong. I wasn't noticing that this was negative and this was positive. So if you get two different things, one going this way and the other going this way, then we say it doesn't exist, period. Just doesn't exist. If they both, from both sides, they went up to infinity, then you could say it was infinity. But in this case, one side, here's negative 1. As you come in this way, as you come in this way from the, well anyway, as you come in one way, it's going higher and higher, but as you come in from the other way, it's going lower and lower. In that case, we just say, no answer, or it does not exist. If you came in from this side and it went higher and higher, and if it came in from this side and it also went higher and higher, then we would say infinity. Okay? That's the way they do that. Does not exist. Okay? Everyone get this, sort of? All right. How about this one? Anybody want to see that? So what happens as x gets closer to 2? Well, if you can, sometimes, it doesn't always work, but sometimes you just put in 2 and see what you get. So if you put in 2, what do you get? What do you get? Well, if I put in 2 here, what's this part equal to? If I put in x equals 2, what do I get? 0, right? This blue part is 0. E to the 0 is what? 1. And then multiply that times 3, what do I get? 3. So it turns out that that's the answer here, is 3. Okay, no, I didn't explain it completely, but that's the answer. Okay, now let's look at these. These are better examples. Or at least I like these better. Okay, so let's do this one. Now, first of all, we need to know what A is. So what is A? 8, right? So this is 8 here, right? Everyone agree? And the height here is also 8, right? Okay. Now, okay, so what's this question asking? Sorry, what's the name of this function, this blue function? He didn't label it, but we assume that it's f, right? We assume this f is this blue function, right? Okay, so what's he asking? He's saying as we get closer and closer to 8, means A here, we're asking what? What would we guess the function's height is? So what would you answer? Minus 16, right? Okay, everyone get it? So that would be the answer, minus 16. Any questions about that? Okay, how about this one? As we get closer and closer to what? Minus 8, that's here. What would you guess the height should be? 8, right? Here. 8. A is 8. Right? Agree or not agree? Anybody disagree? Yeah? Why? What's your problem? I'm sorry, what? Oh, did I make a mistake? Thank you. Okay. I'm sorry, I was thinking it was here, right? I made a mistake. It's here, right? This is A. And sorry, this is minus 8. So, okay, so what's the answer? Minus 8, thank you. Glad somebody's brave. Okay, let's try it again. This picture. As x, okay, first of all, what's A? 2, right? Okay, as x approaches negative 2, means here, right? The answer is what? 4, right? Everyone agree? Okay. How about as x approaches 2? That's here, right? Isn't that here? No. It's here. As x approaches 2, what do you say? Minus 2, right? Everyone agree? The height is minus 2. Okay, how about this one? As x approaches 0. Sorry, A is 7. As x approaches 0. 14. As x approaches 14. 7. Okay, does everyone agree with this? I know that I'm getting a lot of people to answer with the right answer, but that doesn't mean everybody understands it. Everybody understand it? Okay. Now, here's a question we didn't ask yet. We didn't discuss. This one, C and D. We didn't discuss those yet. So what do you think this even means, this question? What do you think question C even means? Or before you answer that, what do you think they mean by this arrow here? What do you think they mean by that? Huh? what do you think they're trying to indicate by that arrow?
It goes on.
It goes on. But goes on how? What? Yeah. Without crossing the x-axis, right? Or in other words, another way to say that, because often we want to talk about the height, so what do we say? That the height never gets to what? Zero, right? The height is never getting to zero. But on the other hand, I think they're also trying to say that it's getting closer and closer to zero. Right? Don't you agree that that's what they're probably trying to indicate with this line? I mean, it's not clear, right? We're assuming that that's what they mean, right? Okay, do you understand? Because they can't draw forever, right? We can't draw all the way to minus infinity. We can't do that. So this is trying to indicate something without actually drawing it, because we can't draw it. So again, what do they mean by this? That it never drops below zero, but this side also never drops below zero, right? According to this, right? I don't think they mean that this is ever going to drop below zero either, right? So this is saying a little bit more than just that it doesn't drop below zero. What's the additional part? That it's getting closer and closer to zero, right? Does everyone agree? Okay, the height. The height is getting closer and closer to zero. So, with that idea, what do you think this question is asking? Because we haven't discussed this question yet. So what do you think, though, it's asking? Can this person here move to some other seat? Yeah, with the striped shirt? Yeah, you. Yeah, can you just move to another seat, that's all. And then a different seat. Different table. Thank you. Okay, so what do you think is meant by this question? What do you think is meant by this question? No? It doesn't, you don't have any feeling for what this might mean? What? The value of what? I can't hear, sorry.
Is that this question asks us to answer that when x equal to negative infinity, what will the value be?
Yeah, right. So, I'm sorry, but can you please move to a different seat? So it means another table. Please. Yeah, he's right. And so, in other words, it's asking what the pattern is here, right? If we moved on forever. And remember, we're interested in the height. The height is really what we're talking about. So what is the pattern of the height as we go, if we moved on forever to the left? That's really what it's asking. So what's the answer to that? Zero. Exactly right. So this should be zero. Okay? Everyone understand that? Now, how about this one? What do you think this is asking? What? It's asking what? As you move to the right, what's the pattern? And by the pattern, we really mean the height. So what do you think this arrow means? I don't think it means that it's getting closer and closer to, what was this, 7? I don't think it means that it's getting closer and closer to 7. I think it means it's going up forever. So therefore, if that's what it means, if that's what they mean by this picture, then what would you say the answer to this is? Infinity. Okay? Is that clear? So now we've discussed what this symbol means and what this symbol means. Okay? So it means, so in this case, the answer was 0 because we think that it's getting closer and closer to 0, meaning the height. Whenever I say it, and we're looking at a picture, we mean the height of the graph. Okay? So it is getting closer and closer to 0. it is going to infinity. Okay, is that clear? Okay, let's try another one. Okay, so how about, let's skip all the way down to this one. How about this one? Can you read that? What's that say? Minus infinity. And look at this picture. So what do you think they mean by this arrow? Do you think they mean that it's getting, by the way, a is equal to 1. Do you think they mean that it's getting closer and closer to 2? No, obviously they don't mean that by that arrow. So what do they mean by that arrow? It means it keeps increasing, right? Forever. So what's the answer to this one? Infinity, right? Everyone agree? In other words, as you go to the left forever, this is going up forever. So it's infinity, right? Remember, we're talking about the height of it. Okay? All right, well now how about if they didn't ask that, but how about if we made this plus infinity instead of minus infinity? Then what would the answer be? Minus infinity, right? Okay, does this make sense? Now how about this one at 2? Again, what is A? A is 1. So at 2 means here. So what's the answer for this one? So I know that some people can answer because I heard them say the right answer, but does everybody get it? Anybody not get it? Okay, the answer is 0. Okay, now here's a simple we didn't discuss yet. This we definitely haven't seen. So I won't ask you that one yet. All right, so let's talk about this now. Okay, so suppose now that we have this picture, this graph. Let's call it F. Let's call this A. Let's call this B. And let's call this C. Okay? Now here's the first question. This one you should definitely be able to answer. F of A. What? I can't hear what you said.
C.
B?
C.
C, okay, C. I thought you said B. Okay, C is right, right? Everyone agree with that, right? All right, now, here's the thing though. This one if you play that game, what are you going to guess? Well, the thing is, you won't have a consistent guess. You won't have a single guess, right? Because the game is, you ask questions close to A. So if you start to ask questions here, you're going to guess what? C, right? But if you start to ask questions from this side, you're going to guess what? B. So you're not going to get a consistent answer. But I didn't tell you one more rule of this game, and that is that you have to get a single answer. Otherwise, you say there's no answer. Okay, I forgot to tell you that, but that's part of the game. So, in this case, are you going to get a single answer? No. So you say there's no answer. In other words, the way you write that is, I just wrote that like that for shorthand, but you say it doesn't exist. Okay? I'm using the book's DNE, but just anyway, it just doesn't exist. Okay? You understand? Okay? Now, however, if I just wrote that, I'm kind of not giving you all the information that I might be able to give you. this just says, oh, there's no pattern there. But that's not really true. There's a strong pattern still. Right? Of course, first I'm going to tell you this. This is giving you some information. And then adding this is kind of like saying, oh, there's no more pattern that I can tell you about. But I don't want to do that. I mean, I'd like to give you some more information. So, I want to say, okay, well, I can't say that if you come from the left and the right, you get a single number. But I can at least tell you that if you come from just the right, you get something. Okay? So what would that be? What do you get if you just come from the right? What do you get if you just come from the right? If you're just choosing these values, getting closer and closer to A from the right, you would guess what? C. So we have a way of expressing that fact. And the way we express that fact is this. We say the limit, still the same function, f, x approaches A, but we have a special notation for from the right. And that is this notation. That means from the right of A only. And if you write that, then the answer is what? If you're just coming in from the right, what would your guess be? C, right? So you'd write C. Okay? Is that clear what that means? And then, you can also say this, of course. That also. Okay? And that will be what? That will be what? B. Right? So that gives, that's better than just saying, oh, the limit doesn't exist. Now I've told you more, right? Okay? So this is useful also. So what does the little plus at the top mean? It means just checking numbers from the right and getting closer. And what does the little minus at the top mean? It means just checking numbers from the left. So this is called the right-handed limit. And this is obviously called the left-handed limit. Okay? But what happened, let's review this one again. What was the answer to this one? It doesn't exist. Right? The limit doesn't exist. This is called the general limit. Okay, so the general limit doesn't exist, but how about the right-handed limit? Yeah, it exists, it's equal to C. And what about the left-handed limit? Yeah, it also exists and it's equal to B. Okay? Now, how about this one? Let's go back to the one we started with, which was this picture. Right? Remember that picture? And let's and what was the general limit? First of all, did the general limit exist, and what was it? Remember, this was basically y equals x plus 2, but it wasn't quite that because, right? But basically it was like this. So we'll use this because it's easy to calculate with. So what's the general limit for this at 2? What's the limit, if this is f, of f as x approach 2? 4, right? This is the first one we did. It's 4, right? Now, how about we never asked about left-handed limits and right-handed limits for this one. Because we didn't even talk about left-handed limits and right-handed limits until just now. But now we can also ask for the left-handed and right-handed limits for this. So how do I write that question, first of all? So this is f. How do I write the right-handed limit? Here. How do I write it? I write x, arrow, what? 2, with a what? A little plus at the top, right? Okay, that's the right-hand limit. So what's the answer to that? It's 4, right? Okay? And now, how about if I want to ask what's the left-hand limit? How do I ask that question? I write limit. You can write lim or limit, doesn't matter. You can write it this way or this way. Okay? So this. Now what? 2 with what? A little minus on the top. And what's the answer to that? 4. So let's look at this. The general limit was 4, right? The right-handed limit is 4, and the left-handed limit was 4. Now let's go back to this one. The general limit didn't exist. The right-handed limit was what? C. The left-handed limit was what? B. Let's say it again. Are the left and right-handed limits equal in this one? No. Does the general limit exist? No. The general limit won't exist unless what? The left and right are the same, right? Because general means that no matter what direction you come, you get the same thing. So it's obviously true. The general limit won't exist unless the left-hand limit equals the right-hand limit. Okay, is that clear? In fact, we can write this statement. If the limit of f of x as x approaches a from the right equals the limit of f of x as x approaches a from the left, then what? You write it for me. If the left-handed equals the right-handed, or the right-handed equals the left-handed, then what? Oh, sorry. And so if they're equal, let's suppose they're both equal to L. Like here, L was here. Okay, so if they're equal, now you finish this. Then what? Then the general limit will also equal L, right? And how do I write the general limit? I don't use the plus or the minus, right? So I just write what? The limit as x goes to a of f of x is equal to L. Okay? That's a theorem in calculus. That's a theorem in calculus. Okay? Now, how about if I ask you the other direction of this statement? The other direction means, like if I say, if today is Monday, or what is today? Tuesday. We have business math. Sorry, then we have business math, right? That's an if-then statement. By the other direction, I mean, if I tried to say, if we have business math, then today is Monday. Okay? That's the other direction of this. This is an if-then statement. So, like in logic, might call this one P, and then this one Q, and then this if-then would be written like this: P implies Q. Okay, that means that you could read this as if P, then Q. It's just a symbol for that. If P, then Q. If today is Tuesday, then Q. Then we have business math. So how would you read this statement? If Q, then P, right? Which is what? Q is what? If we have business math, then today is Tuesday, right? So is that also, this is a true statement, right? This one I just wrote. That's a true statement. If today is Tuesday, well, it's usually true, not always. Next year it might not be true, right? But this year it's true. How about the other way around? How about Q arrow P? If we have business math, then today's Tuesday. I think that's also true, actually. Right? If we have business math, then it's Tuesday, right? Because actually we have a class on Saturday, so it's not quite true. Okay, so therefore, this doesn't always mean, if this is true, it doesn't necessarily mean that this is true, right? Another better example is, if I live in Beppu, then I live in Japan. Okay, that's true, right? If you live in Beppu, you live in Japan. But reverse it. What does it say? If I live in Japan, I live in Beppu. That's not necessarily true, right? So just because one direction is true, doesn't mean the other direction is true. And in math, they write that like this. If, I can't remember anymore actually. Oh no, sorry. It's written like this. P, if, Q. That means both directions. This means P arrow Q and Q arrow P. That's a way to write both directions. Okay? So that means P arrow Q and Q arrow P. Okay, so that's just a notation in math. Okay? But obviously, that's more than just saying P arrow Q. Right? P arrow Q and Q arrow P are not the same. So if you say they're both true, you're saying more than just the first one is true. Right? So this is a stronger statement than just this one, just that one. Okay? Now, going back to here, we have this theorem, actually. This is actually a theorem. Let's review it again. What did it say? Where's the P? That's the P. And here's the Q, right? So it's, if this is true, then this is true. Right? Now how about the other direction? If this is true, is this also true? So what do you think? If the general limit exists, and it's equal to L, then what? Does the left-hand limit have to equal the right-hand limit? Yeah, it's pretty obvious, right? So yeah, this is also true. So actually this goes both directions. Okay? So that's a kind of more, it's a stronger theorem than if it only went in one direction. Okay? So now, with that understanding, what about this question? Now this is kind of, anyway, so what about this question? So what is it asking? Only if you come in from which side? From the right side, and getting closer and closer to what number? 0. So it means we're coming in this way and asking, is there a pattern for the height? So what's the answer? Sure. What is it? A is equal to 1. What is it? 2. Right? So the answer to this is 2. Okay? Agreed? And now what's this question? If you're coming in from the left, what's happening to the height? Minus 1. Minus 1, right? So this would be minus 1. Okay, finally, this one. Finally, this one. So this says, does the general limit exist? But the only way the general limit exists is what? If the left-handed limit equals the right-handed limit. Now the left-handed limit was what? -1, and the right-handed limit was what? 2. But -1 is not equal to 2. So the left-handed limit is not equal to the right-handed limit. So the general limit, what? Doesn't exist. Okay? And how about this? F of 0 is what? Can you see this graph or not? Where's the filled in part? Is it here or here? It's up here, right? Can you see that? Where's the filled in part? Here, right? So what's F of 0? 2, right? Okay, so this would be 2. Okay? Everyone understand that? Okay, and we did this one already, right? We already did that. Yeah, thank you. Okay, any questions about this? How about this one? I'm getting tired of this. How about this one? A is equal to 4. As x approaches 12, 4, 8, 12. As x approaches 12, it looks like it's 4, right? Okay, I think we'll stop with this. I think we've done enough. Okay, but you could do all these other ones. In fact, you will do them all if you haven't. But this one is a little more. So let's take a look at this one. A little bit newer. A little bit new. So, first of all, what's A? 6. Okay, now, let's just look at this one. Now you can use the word infinity. Okay? So what, it's pretty clear what they mean by this arrow, right? They mean that it what? Goes up to infinity. Right? By the way, what's an example of a function that does something like that? How about this function? Let's look at some of those. First of all, what's this function look like? That doesn't quite look the same as the picture. That looks like this and like this. Because as x gets closer to 0 from this side, this is getting very small, so the whole thing is getting very large, but it's positive. Right? But if you come in from this side, this is still getting very small, close to 0, but always it's negative. So the fraction is going to be negative, so it's going to be negative infinity. Right? So it goes down. Okay? However, how about if I gave you this one? What's that look like? Now, is it ever negative? No, it's never negative. Now, as you get close to 0, what happens to the bottom part? It's getting close to 0. And the top part is remaining at 1. So when you have 1 divided by something really tiny, that's a large number, right? So it's also something like this. In fact, it grows more quickly. But on the other side, it's not negative. So it's also like this. Okay? So let's use these two instead of that picture. Let's call this one F and this one G. So if I ask you this, the limit as x goes to 0 from the right of F, what's the answer? Infinity. As you go to 0 from the right, it's going up. Right? So we write that as plus infinity. You can't use that symbol in the online system, so you have to type out infinity. But usually you'd write it like that. Okay? And how about this question? It's not infinity, it's minus infinity. Okay? Like that. Everyone understand? Now how about the general limit? So remember we said that they have to be equal in order for the general limit to exist, but minus infinity and plus infinity are not considered equal, so we would say doesn't exist. Okay? Now how about this one though? G. Plus infinity. And how about this one? Right, going in from this side, it goes up. So this is also plus infinity. So this one we're allowed to say, now, some people would argue with, I mean, some books might say, no, you don't say this, but anyway, it doesn't really matter. It's just a question of how you want to make the word. But anyway, okay, anyway, they're going to say this. Okay, because they're both the same. Okay? All right, everyone understand that? By the way, we can ask a couple other questions as well. For example, for F, I could ask this. That means what? As x gets larger and larger, is there some pattern? Or looking at the function, as x gets larger and larger, what happens? The whole thing gets smaller and smaller, getting closer and closer to 0. Right? So, that's the answer. Okay, same thing with this one, right? As you go this way, it's getting closer and closer to 0. Remember, when we say it, and you're looking at the graph, it means the height of the graph. Right? So the height is 0. Even if you went to the left, it's also 0. So you could also write this. So for this one, as x gets larger and larger in this direction, moving to the left, what happens to the height? Getting closer and closer to 0. Right? So that's also 0. Okay? So we can say all of these things. All right? Okay, let's go on to another section. Okay, we have to talk a little bit more. We don't have much time to do this. So we have to talk about one more thing. And that is the word continuous. I have to do this quickly. So we had some functions like this one, and versus, say, this one. And if you were going to use continuous to describe these functions, would you say that the left one or the right one is continuous? I think most people would say the right one is continuous and the left one isn't. Okay? So we have some kind of intuitive or natural feeling for what we mean by that word, but we want to give a mathematical definition for it. Now, we just learned about a new tool called limits. The question is, can we use that tool to help us nail down a definition for continuous? Now, one thing is, we don't say continuous by itself. We say continuous at a particular point. So I could say, is this continuous at A? I could say, is this continuous at B? So most of us would probably agree this is not continuous at A, even though we don't have a definite idea, a definite definition of continuous, but still I think most of us would say this is not continuous at A. Most of us would say this is continuous at B. But also, I think most of us would say this is continuous at C. Okay? So we don't just say continuous, we say continuous at a particular point. Okay? But we still don't have a definition for it. We can kind of agree, but if we don't have a definition, that's not good enough for math. Okay? So we have to have a definition. So let me draw a few pictures and see if you can. So let's draw, first of all, this picture. No, sorry. First of all, this picture. So is this function continuous at A? Do you want to call that continuous at A? No, I don't think you want to, right? So why not? Well, I could say that it's not even defined at A. Okay? Do you see that it's not defined at A? F of A is not defined, right? So let's make the first condition for being continuous at A that the function is defined there. If it's not defined there, we're never going to say that it's continuous there. Okay, so first of all, we want to say, so we'll say F is continuous at A, at x equals A, and now we want to make this definition. If, and the first part is at least F of A should exist. Right? If it doesn't even exist at A, we're definitely not going to say that it's continuous at A. Okay, but is that enough to make it continuous? Well, how about if I did this? I'm sorry, let me make a new picture. How about if I did this? Do you want to call that continuous? First of all, does F of A exist here? Yes, it does, right? But do you want to call that continuous or not? Is that enough? No, I don't think most people want to call it continuous at A. So that just saying that it exists at A isn't enough, right? So what else should we add? Well, how can we use the tool that we just learned about to say something about F of A? Or I'm sorry, near A. Or say something about A and F. What tool? We just spent the whole hour and 15 minutes talking about a tool now, so let's use it here. So what can you say here? The general limit here, what? Doesn't exist. Okay, so let's say part 2 of our definition is, or the second condition is, the limit of f of x as x approaches A should exist, right? The general limit should exist, right? Okay? Okay, is that enough? Well, let's look at this. That. Does the general limit at A exist or not? If you come in from the left and you come in from the right, do you get the same thing or not? Yeah. Right? If you come in from the left, you get what? B. If you come in from the right, you get what? B. So the general limit exists, right? Is this continuous? You want to call this continuous? Oh, and sorry, does it meet condition 1? Does f of a exist? Yeah. Does it meet condition 2? Yes. Okay, so let's call this continuous. No, but we don't want to call that continuous, right? So this is not enough either. These two by themselves are not enough. Let's try for a third condition. Okay, can anybody give me the last condition? Oh, very good. What? Good. I don't think I would have gotten that. Limit as x goes to a of f of x should equal f of a. Right? Okay? Why? What does that do? That pushes this down to here, right? 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 Basically, that pushes this down to here. So if that's true, then you won't get this jump up here. Right? The general limit, what you get on the limit, and what you get at the actual value are the same, then you don't get a jump. Right? So these three together are the mathematical definition for f being continuous at a point a, at a value a, at x equals a. Okay? Now usually what they do is they only write this condition. It's a little bit annoying, but here's the reason they say that. I never really like this, but here's the reason they say it. They say, if you write this, if you write this, you can only write this if this exists. That's what they say. It sounds a little like cheating to me, but they say, you can only write this if this exists, this part here. Okay? So that if this exists, it means it's a number. Okay? If this is a number, then you're saying that this equals a number, therefore this exists. Okay? And then if they're equal, that's condition 3. So this actually encompasses all 3. But anyway, that's what most books will do it that way. But this is really clearer. It has to be this, this, and this. Okay? So now we know what we mean by continuous function. Okay? So this function is not continuous at a. This function is not continuous at a. This function is not continuous at a. But this function is continuous at a, right? Let's just confirm that. Does f of a exist? Yes. Does the limit, the general limit, exist? Yes, the left-handed and the right-handed are equal. And does the general limit equal the actual value? Yes. So therefore it's continuous at A. It's also continuous here and everywhere. And this one is continuous almost everywhere, only at A is it discontinuous. Right? So we talk about continuous at a point. We don't just say continuous. We have to say continuous at this point, discontinuous at that point, and so on. Okay, that's all for today. You will have, I'll send you homework. I'll extend, if I didn't do it already, I will extend last time's homework so that you can still work on it. You'll have like 4 extra tries to do. You don't have to do it if your score is already high. You can leave it as it is. If even if your score is high, you can still do it, and it will automatically choose your highest score. So if you screw up now, it won't hurt you either. Okay? But it's up to you. And then I'll assign new homework, and then next week I'll also have a big homework assignment. And then you'll have now the homework assignment will be actually due after our exam, but the exam will include problems from that homework assignment. And just to explain again, how do I make exams? I have to say, I shouldn't admit it on the camera, But I'm really lazy when I make exams, and all I do is go through the homework problems that I've already assigned, and copy, and paste into a Word document, and print it, and carry it to class, and hand it out to you. In other words, you're not going to get problems that you haven't seen already. You're not going to get problems that you haven't done already. I'm not going to do that. Okay, I'm too lazy. So, if you do the homework and you understand it, and you don't ask somebody else to do it for you, then you're going to do well on the, hopefully, you should be able to do well on the exam we'll have, which will not count much at all. I have to check our syllabus, but I hope to only count it like 10% of your grade. I have to make sure I didn't say anything other than that in our syllabus. But the final exam is a big, big weight. It counts 50% of your grade. So if you don't do your homework yourself, your score on your final exam will pull your grade down a lot. So don't ask other people to do your homework. If you're having questions, we have extra help sessions on Monday, Tuesday, Wednesday, and Thursday? No, just Monday, Tuesday, Wednesday, 7th period, which means now, in room what, F108, in room F108. So you can get help that way. If the TAs can't help you, then I can help you. And we also have usually the video of our class, so you can go through it and check that also. But I really hate when I get the students who have like a grade of 95 on their homework, and they get a grade of 42 on their final exam. And it happens. And then I have to decide, should I fail them or give them a C when they're expecting an A or an A plus, right? I really hate to do that. It's not fun to fail students, but I have to do it because I have to do it. But, so I wish that you don't ask other people to do your homework. Because if you do, you're going to fail the exam. And if you fail the exam, you could fail the course. And that's not good, I guess, for most people. Okay? So I urge you to do the homework. Okay?